In Chapter 3, we are going to focus on what we call functions. But in Section 1, we're not going to quite get to the conversation of functions yet. We're just going to focus on what we call relationships. So in this section, we're going to talk about describing a relationship given a graph, and can we sketch a graph given the description. So we start here in this example with a simple graph of temperature throughout the day. So we've got midnight to midnight. So obviously, a lot of times the experience is once the sun comes up, we get an increase in temperature, and then as the sun goes down, we decrease in temperature. Now I know sometimes that's not always the case, but let's just think about this as an average day. So it says in segment 1, the temperature from midnight to sunrise stayed constant. So it looks like then right here that this would be sunrise. And then section 2 shows something different. A lot of us have an instinct about reading a line graph and interpreting it in terms of, real life experiences. So segment 2 goes up from left to right. So we would assume that means that the temperature increases. Line goes up, temperature goes up. So based on the time frame, give a possible explanation for the change in temperature. Well, if sunrise is here, right in the middle between 1 and 2, we can assume that the sun starts warming. The ground and air, however you want to talk about it. So again, this is kind of our normal experience. Sun comes up, gets warmer. So which segments of the graph show decreasing temperature? Give a possible explanation. Well, again, our instinct would say these two sections here, section 4 and 5, because they are going down from left to right. So what might cause the decrease in temperature? Could be a cold front, could be lots of different things, but if we assume that this is kind of a normal day, probably the sun setting would cause a cool down. So sun no longer can provide heat since it's going down, it's getting farther away, so we have a cool down. So if we were to think about, instead of just using our instinct, thinking about it in terms of mathematics and graphs, how could the slope of each segment of the graph be related to whether the temperature increases or decreases? As a review about slope, slope is rate of change. It is a steepness or tilt of a line. So 1 does not have a slope, it's flat, there's no tilt. Segments 2 and 3 have a positive slope, and then segments 4 and 5 have a negative slope. So we can say if there's a positive slope, the temperature is increasing. If we have a negative slope, the temperature is decreasing. I'm just going to abbreviate here. Okay, pretty simple. Now let's look at a situation where we have 3 different scenarios and then 3 different graphs. So we're supposed to match them. First day, so September 8th, it rained very hard during the morning, but then rained less and less as the day went on. September 19th, it rained steadily all day. September 27th, it rained lightly during the morning, but then rained heavily for the rest of the day. So now let's look at these graphs and let's talk about their slopes and then see if we can go back and match it with the day. So we're talking about rainfall. That means that when we measure, and some of you guys might have this at your house, a rainfall gauge, or if you listen to the news, they might tell you to expect, say, 1 to 2 inches of rain that day. So as it's raining, that rainfall gauge will be increasing as the day goes on. So in graph A, if you were to watch the rain gauge, it would be increasing at a very steady pace. So this is a steady increase because we've got a positive slope. Now in B, we don't have a straight line anymore. We have a bit of a curve. So again, if we were to watch that rain gauge, it would start out filling up slowly. So start slow, then that rain gauge would fill up really fast. Then we would increase faster. Graph C, we start out with the rain gauge filling up quickly, so start fast. And then the rain gauge is still filling up, just not as quickly. So then we increase slower, or more slowly, however you want to say it. So now it might be pretty easy to match it up with the day. So the steady increase day looks like it's September 19th. And then where we start slow and then rain faster looks like September 27th. And then the quick starts very hard and tapers off is the 8th. All right, so we've now matched some different situations with graphs. Now let's see, oops, getting a little ahead of myself. Let's talk about this reflection question here. Could we have a situation where it's raining throughout the day and the graph slant down from left to right? Well, if you think about it, if it's raining, will the rain gauge magically, so let's say before it starts raining, we've got some water in the rain gauge. Then as it continues to rain, that water level magically goes down. That's not going to happen. So if it's raining, the rainfall will always increase. Okay, again, if you think about the water on the ground, it's always going to increase if it's raining. Now let's see about sketching a graph from a situation. It says a pool in a community park is being filled for the summer. A water truck arrives early in the morning, but no water is put from it into the pool for 1 hour because a small repair must be made to the pool first. The spigot on the water truck is then opened partially to add water gradually to the pool during the next 2 hours. So we're supposed to sketch a graph showing the height of the water in the pool over the first 3 hours that the water truck is at the pool. So what I would do is I would go back into the problem and separate it perhaps into different events, different types of situations where we're filling the pool. I see this second sentence looks like it might be important. It says a water truck arrives early in the morning, but no water is put from it into the pool for 1 hour. Can't really graph the reasons for why, just the fact that it is. So, how do you think that would make it look on the line graph? If there's no water being put in for an hour, we have nothing on the graph until hour 1. So you can either leave it blank, or you can fill it in that it's still at the level of the horizontal axis. And we should probably label this horizontal axis. It's time in hours. Okay. Now the second situation looks like the last sentence. The spigot on the water truck is then opened partially to add water gradually to the pool during the next 2 hours. So we're going to increase, but somewhat slowly. For the next 2 hours, so that would be from hour 1 to hour 3. So up something like that. Okay, pretty simple. Then it says, the workers determined that the repair they made to the pool is working, so they completely opened the spigot on the water truck to continue filling the pool. How do you think this will affect the water level in the pool? Well, think about it. Again, just common sense. If you start out with the spigot not open very much, and then you open it all the way, then the pool's going to hopefully fill up faster. So the water level will increase more quickly. So how can we show that on our graph? So we started out, first hour, no fill, so flat. Then for the next 2 hours, filling, but very gradually. And then the spigot's opened all the way. So it's going to increase, but faster than it did before. Okay, and then they want us to stop at 6 hours. So that's what it could look like. Again, pretty simple. Let's take a look at this situation. It says a hot air balloon rises as the air inside it is heated to a temperature greater than that of the surrounding air. During a balloon trip, the pilot controls the height of the balloon by adjusting the burning of propane fuel to change the temperature of the air inside the balloon. The graph shows the height of a balloon over time. So just take a second, look at that graph there. Looks like we've got 4 phases. It says, during which phase is the change in height the greatest? Explain. Well, again, pretty much common sense here. Looks like that would be phase 2. Because it goes up the steepest. So we start here at the beginning of phase 2, and here that's a pretty big jump from left to right. So shows this, and if we talk about slope, positive slope shows the greatest positive slope. Number 2, it says what happens to the balloon's height during phase 4. So here we have a situation where something's decreasing. So earlier we were talking about water level. You can't really decrease water level unless you take water out, like siphon it out or something like that. So here we're talking about height. Phase 4 is the only phase where we see a decrease going down from left to right. So that would mean it'd have to be where the height decreases, because we have because it shows a negative slope. Okay, so the main things you want to remember here in this section: slope, positive, going up from left to right. Whatever unit of measure you're thinking about, water level here, height, could be lots of different things. That means whatever that is increases. Slope is negative, goes down from left to right, decreases. Simple enough. Now in section 3.2, we're going to continue to talk about relations, but we're going to start the conversation of what makes a function a function. So in the last section we were talking about what we call sets, a collection of items. But most of what we were talking about had some kind of unit of measurement in relationship to time. So time, in a sense, was a set. You could have 1 hour, 2 hours, so on and so forth, and then our height or our level of water, whatever. A function pairs each element in one set, called the domain, with exactly one element in the second set, called the range. Some of you have probably heard this phrase: for every input, there is only one output. Okay? So here they show us a function relating a number with its square. So if I take a number and I square it, is there only one possible answer I could get? And the answer to that is yes. If I square 2, the only square of 2 is 4. So each of these numbers in the domain, we square them, and we get our range values. There's a way that we can write the relationship between a domain and range using what we call function notation. Now this is going to look strange, just like when I showed you set builder notation, that looked strange. But this notation is something that is used very, very often in a lot of math classes. So after Algebra 1, you're going to use this a lot, and we will probably use this quite a bit in Algebra 1 itself. So it looks like this, f parentheses x, and what that's saying is it assigns a function the output value in the range to this corresponding input value x from the domain. So domain input, range output. So we perform a function on the input, we get an output. Now this does not mean f times x. This is read f of x. The function performed on x is blank. Okay, here's another way you can think about it. So if we see f parentheses 3 equals 9, that's saying the function performed on the input of 3 gets you an output of 9. And that's what we got here. So if I wrote, say for example, f of 2, the answer to that would be 4. Because the function performed on the value of 2 gets you the value 4. So that's one way that you can write or show the connection between the input and the output of a function. Now what they're going to show us in Reflect 1a is reminding us of what we've talked about earlier, set notation. We used set notation when we did inequalities. But this is a lot simpler than the set builder notation we were using earlier. It does use the curly Q brackets, but here we just list the numbers. 0, 1, 2, 3, 4. So if I want to give the range in set notation, I would do the same thing. Just use the output values, the range values. So if I look at f parentheses 4 equals 16, and interpret what it means in terms of input and output values, it means the function performed on the input value four is the output value $16. Quite a long sentence that can be represented in a very short equation. That is the beauty of function notation. Now let's talk about the definition of a function. Suppose the 3 were paired with the 4 instead of the 9. Would the pairing of the two sets still be a function? Why or why not? So instead of 9, I put a 4. Is this still a function? Well, let me repeat our definition. For every input, there is only one output. I just realized here, that doesn't make sense. It should say input. There we go. You were probably wondering about that. So, does 3 only have one output? Yes. Does 2 have only one output? Yes. Now, what you might be thinking is, wait a minute, they have the same output. That's fine. There's nothing in the rule that says for every, oh, I guess I wrote it twice. Never mind. For every, oh, I remember why that was written there. Because we said output for range. Okay, that makes sense. All right. Anyway, here we go. It doesn't say for every input there's only one output, but it can't share that same output with any other input. It doesn't say that. It just says for every input we get one answer. So if I look at the numbers on the left, do I have one arrow pointing to one number? So yes, we do. Now let's take, so this is a function. Still only one output. Now let's say we had 3 was paired with the 4 and the 9. So instead of that, let's say we have 2 arrows coming from 3. So 3 has an output of 4 and 3 has an output of 9. There we have a problem. So we have an input of 3 going to 2 different outputs. That is not a function. So, because we have 2 outputs. So if you pair each, let's say for example, you pair a month with the possible numbers of days in the month, will you get a function? Why or why not? Let me rephrase the question. For every month, is there only one set of possible days in that month? So for the month of January, how many days are there? 31. Month of February, how many days are there? Well, some years it's 28 days, some years it's 29. So do I have the same so do I only have one output for each month? Well, February messes it all up. So no. Because February, which is my birthday month, by the way. Now, because February can have 28 or 29 days, depending on the year. Okay? All right, we're going to do one more page in this video, and then you'll have to go to the second part video to finish up these notes. So here are some other words that we can also use with domain, range, input, output, and that's independent variable and dependent variable. Independent variable, that's the input or the domain, what we put into the function. Dependent variable is the output or the range. Okay? Now, whenever we do something to a number, that's called the function rule. So if we think about what we did on the earliest page, we found the square of each of the domain values, each of the input values. So a function rule, for example, would be what's on this side of the equal sign. So I square the numbers. So if I know a value for the independent variable, which in this case would be x, which you put into the function, you can use the function rule to find the dependent variable, the output. So here's how a function could be written. As the cost of sending m text messages at 25 cents per message can be represented by the function. Again, this is not C times m, but we would call this C of m equals 0.25 m. So it says complete the table for the given domain values. Write the results as ordered pairs in the form independent variable, dependent variable. So what they're telling us to do is to plug in into this function here my input values, perform the function rule, which in this case would be multiplying by 0.25, and so then write it as an ordered pair, input, output. Later on we're going to graph these points. So I'm going to keep going. 2 times 0.25 is 0.5. And this is 0.75. And the last one will be 1. Okay. I think actually what I'm going to do is I'm going to stop here just because of where I'm at right now today. I have to pause this video. So after you've finished filling out the table, which you probably have already done that, go find part 2, video part 2 of sections 3.1, 3.2, 3.3.